we've hit chapter 15, and this particular PowerPoint is over sections 1 through 4. I do want to point out some acknowledgments before we get started. All the materials being used from Pearson's Hibbler PowerPoint presentation, that some of the materials are there. You can tell which ones those are because that's in the Times New Roman font. And those are being used with permissions. I'm going to use some GIFs and images that are not mine. But on each of the ones that aren't mine, I am referencing the location where those GIFs are. So while you were watching and listening to those acknowledgments, you see this one from Flipping Physics, because what we're talking about here is impulse and momentum, and we're going to start looking at collisions. So if you guys remember, or if you had me for physics, we looked at collisions back there, and we talked about momentum. And in momentum, it's kind of one of those things that a lot of people get it, and it's really easy to understand for them, and for some people, it's a little more complex. But remember that momentum is an interesting concept. It's that mass times velocity. And when we defined forces way back when, we talked about Newton's second law. And Newton's second law actually said that impulse was equal to a change in momentum. And we're going to use that form of Newton's second law to really, really help us out as we go through that. So let's look at this GIF for just a second. We've got a collision that's caused the ball to bounce, and we're looking at that impulse. And one of the things that we can see from a graph is that the impulse is going to be the area under the curve. And we're going to come back and look at that graph and see how that works. So let's go back to what our textbook author says. So we're going to talk about that principle of impulse and momentum, and it can be applied to problems involving both linear and angular momentum. So think for a second, linear momentum is a ball hitting a wall, or our trains colliding, or carts on a cart rail. But if I'm doing angular momentum, remember the skater spin, where the skater's arms are out a little further, and then when I come in and tighten up, that I'm going to have that change in angular momentum, but angular momentum is conserved, but I get a change in the speed of the spin. And I can also look at those in terms of collisions as well. So this principle is useful in solving problems. We're still dealing with force, we're still dealing with velocity, we're still dealing with time, and we're going to look at some impact as we get towards the end of this chapter, really kind of look at that. So the principle of linear impulse and momentum, and we can look at it in terms of integrating the equation. And if you think back when we defined Newton's second law, I always go back and said, instead of saying that the second law is the sum of the net forces is equal to mass times acceleration, I said, wait a second, Newton really said that impulse was equal to a change in momentum. And when we look at that particular aspect, we can get our impulse, and remember that our impulse was defined as the force times the change in time, and we can look at this change in momentum. So that's very important. So linear momentum, which we use mv, it's a vector quantity, and we're going to use things like L to denote that. The vector's in the same direction as v, and linear momentum has strange units, kilograms, meters per second, or in the English system, it's slug feet per second. And impulse is that integral of our force times the change in time, is the linear impulse, and we're going to denote that with the letter I. I is impulse, kind of makes sense. It's also a vector quantity, and it makes it pretty clear that the area under our curve is going to give us that impulse. So the area under the curve is going to give us that impulse, and remember the GIF that we started. If I have a constant force, then I'm just going to end up with a graph that looks like this. Again, the area is under that spot. So let's think about this for a second. Let's rewrite the equation a little bit so that we can look at this in terms of initial momentum plus my impulse is going to give me my final momentum. So think for a second. I got a hockey puck sliding across the ice. It's going to get an impact with the stick, and it's going to change its momentum, and it's going to go off with a final momentum. So we can rearrange our equation where I get my initial momentum, I apply the impulse, and I end up with a final momentum. And we can see that in terms of a diagram here. I've got my hockey puck going off in this way. It's hit with the hockey stick going that way, and we change the motion of that hockey puck that's going down into a new spot. And just to kind of look at it, the momentum diagrams, we can split them up. We can take it in terms of our various coordinate systems. I can do it in terms of the x coordinate, I can do it in terms of the y coordinate, and I can do it in terms of the z coordinate. And so we can really look at this, and because they're vectors, we know that we can write these kinds of things out. But I want to make a key point here, and we know that it's not the fact that you're falling off the building, it's the sudden impact at the bottom that kills you. Remember, for those of you who had me in the engineering physics class, remember that I usually show a NASCAR video talking about a safer barrier. Remember that safer barrier, it's going to extend the time of the collision, which means the forces on the body on the driver are going to be reduced. I can have the same magnitude, but I can extend that time and I'm going to reduce those forces. If I'm on the interstate and we see the various cable barriers or the various drum barriers in front of the concrete, by extending that time, the experienced force can be reduced. So the ultimate impulse is going to be the same, the magnitude of that impulse, but the forces that I'm going to feel on my person are very, very different, and that can be the matter of difference between life and death. Same thing happens with your seatbelt, because and that extends the time so the forces are reduced. So we want to make sure that we're looking at. So the areas under the curves are the same, the magnitudes are the same, but the physical result is going to be significantly different. And that was one of the big things that we talk about in terms of impulse. So let's do a couple quick calculations. And for reference, I want you to look at the preliminary problems for section 15-2. And these are a couple that we can look at. So I've got situation 1. I've got a box that's been applied with a force of 100 newtons. It's sliding down the inclined plane. And we want to determine the impulse. The impulse is going to be a force times the change in time. Again, in this case, we've got a constant force, so I don't have to do any integration. And so it's just going to be my 100 newtons times my 2 seconds is going to give me my 200 newton seconds. And I'm going to do a quick unit analysis to show you that those newton seconds are going to have the same unit analysis as if I were doing momentum. Remember, momentum is mass times the velocity, and that's kilograms per meters per second. A newton is a kilogram meters per second squared. I've got my multiply by my seconds, and then those are going to cancel, and I'm going to get a kilogram meters per second, which is going to be the same set of units as I get for my momentum. So let's look at a situation 2, and this time we're going to use it with a graph, all right? So I've got force on this side, I have time here. We want to find the force at time is equal to 2 seconds. So if we've got this part, here's my first part, and then here's the second part. So from 1 to 3 seconds, we're going to get a constant force applied, and we're looking at this force that's being applied to this block is actually interpreted by this graph. So all I have to do is find the area under the graph. So I get 1/2 the 20 times 1 second, and then I'm doing it for 2 seconds, so it's just through this first part of the area. So that's my 20 newton force times my 1 second. I add the two together, and I'm going to get 30 newton seconds. So we can look at those preliminary problems, and I encourage you to go back and look at the preliminary problems. I encourage you to go and look at the tutorials that are in the homework assigned problems, because that really gets us looking at this particular aspect. So how am I going to go about solving these problems? Well, it's like we do with all our problems. We need to first, even though we're not going to do a free body diagram first, get a good picture of what the problem is asking. Am I along an inclined plane? Am I in some strange curvature coordinate system? Am I going to be in an XYZ system, or am I going to be in an R theta system? You really want to establish your coordinate system that you're going to look at. So most of the time, my first rule of thumb is draw your picture. And once you've got your picture drawn, then maybe we can look at the individual free body diagrams. Okay, we want to look at those free body diagrams. But even then, we want to establish that coordinate system. Remember, if I have an inclined plane, the coordinate system I want to set up is that I put one of my coordinates along the inclined plane and one of my coordinates perpendicular to the inclined plane. Then I can take a two-dimensional problem and quickly make it a one-dimensional problem because I've changed my coordinate system in my favor. So when you're analyzing your problems, really, really look at the coordinate system that's going to help you out. We want to draw our free body diagram. We want to write the information that we know. And we may want to look at impulse and momentum diagrams. And we'll talk about that in just a second. We may want to look at how this is going to sequence through. And we'll really talk about that as we go through here. We want to resolve the force and velocity into our x, y, and z components, or our r and theta components if we're in that angular situation. We may want to be able to look at that. And then we're going to use our principles of linear impulse and momentum to help us out. And then we want to look at our forces as a function of time. In Engineering Physics 1, we didn't allow for variable forces. Now that's why we take this a step up, and we can now apply those variable forces. And depending on what we're looking at in terms of those variable forces, we might want to break the problem up. And I've got an example that's actually going to show how we might want to break that problem up. So that's what we're going to be looking at. And I want to remind you that in your text, right before the problem sections at each place or right before the examples, your author does give you a problem-solving strategy so that you can actually look at it. But here's the same problem-solving strategy that we're going to look at. So I'm going to do a real simple problem. I got a 20-pound block that's sliding down that inclined plane, and you're going to use a 30-degree inclined plane. It's got a coefficient of friction of 0.3 and an initial velocity of 2 feet per second. And we want to know what the velocity is after 3 seconds. Now, we're not actually talking in this case about that impulse like we would normally think of, but we can use that same idea to help us with our problem. So the steps are establish my coordinate system and draw my free body diagram. So I draw my free body diagram. We're going to use a coordinate system that's along the plane and perpendicular to the plane so that we can look at it that way. And I'm going to calculate the force that's parallel to the plane or along the plane. So I've got the mass of the weight of the block, which is 20 pounds. I've got my angle, the 30 degrees, and I have to account for my normal force. Remember, friction is fun because my force due to friction is equal to mu, which looks like a U, times my normal force. So I'm going to get that. So I get the force down the plane. And in this case, that's going to end up being 5.67 pounds. So I'm going to set up those equations. Now I'm going to use that impulse and momentum system. I'm going to look at my initial momentum. I'm going to look at that, quote, impulse that we have. And I'm going to look at my final, and we're going to solve for the final. Now, because this is in the English system, I need mass. So I'm given that it's 20 pounds. I'm going to have to divide by the acceleration due to gravity, which is 32.2 feet per second squared. I have my initial velocity of 2 feet per second. I've calculated my force down my inclined plane, and we're wanting to find it after 3 seconds. So that's essentially my impulse. And I'm going to end up with the mass times the final velocity. And when I do this and rearrange it and I solve for that velocity, I get that it's 29.4 feet per second. So you can use that idea to actually work through the problem. So let's look at another problem. And this time I'm given a 400 kilogram object that's being towed with the force described by the graph. Now, this is one of those cases where we don't have a constant force. We got a constant force that's being applied here, and then we're going to change with respect to time here, so we can break this up into 2 parts. But I know that if I want to find the final velocity, I can use that impulse and momentum idea. My impulse is the area under the curve, right? And I'm going to get that it's going to be equal to my change in momentum. So if I want to find the final velocity at 8 seconds, I can do that. And I'm going to use from the area, use my change in mass or change in momentum, and I can actually calculate in terms of meters per second. So if I've got that graph, hey, life is super easy, right? I can just get the area under the graph and I've got my problem solved in a couple of steps. So you think of those problem reflections and rethinks, those particular type of an idea. Well, this is one way to do the problem if I've got the graph. Well, now let's kind of approach this problem differently. And let's see the other process. Now, the other process is going to be a little bit more gory, but we want to be able to see how that would work. And the other process may be able to give me a little bit more information. So I'm given my graph. We see that I don't have a constant force. So I'm going to have to break this up into the 2 time segments. I got to break it up in the 0 to 5 second segment, and I've got to break it up in the 5 to 8 second segment. So here in the 0 to 5 seconds, the force, I've got that it goes to 600. I need the slope of this line. Voila, there's the slope of this line times my time, and that gives me my force. Okay, we're going back to looking at it from this part right here, right? I get this part. Now I'm going to integrate from 0 to t, and that's going to give me my mass times my velocity. Mass was 400, so that's where that 400 comes from. I can solve it, and I end up with my velocity at the end of 5 seconds as being 3.5 or 3.75 meters per second. Now I'm going to go through this same part, but remember this time I've got to account for where I start and where I finish. So I'm going to end up with this particular portion of it, right? Going to end up doing the same type of an analysis. I'm going to solve for my velocity here, and at 8 seconds, when I plug in time, I end up with my velocity value being 8.81 seconds, which is the same answer that I got from looking at it just by doing the area under the curve. So again, you're looking at what you're having to make sure of when we're dealing with these things, okay? So you want to make sure, and you want to look at your F equal ma equation. So now if I want to find the distance traveled, well, we just take it that next step, but I can't just do it directly because I don't have a constant acceleration. Remember, I have 2 different parts. I can't use it because it's not constant. All right? Can't use it because it's not constant. And we go back and we plug in our term for velocity, and we do the same thing here. This is from our 0 to 5 seconds. We can plug this in, we get it, and we can solve for the ultimate distance. So I encourage you to go and look at a couple of those example problems that are in the book. I am going to work some additional examples, and those will be in the worked problem section of our Blackboard. But I wanted to get this theory point out. So for more examples, see the individually worked problems in Blackboard, and I strongly encourage you to look at the sample problems that are in the text. So now let's kind of take it one step further. We know that when we're dealing with these problems that we have to look at the center of mass. If I've got a particle, no brainer, right? My particle doesn't necessarily have size. I don't have to worry about taking size into account. But as we start using real systems, I've got to worry about where that center of mass is in relationship to how the collision is going to interact. Think of 2 cue balls. Cue balls, we know if I take those cue balls, we're looking at where that center of mass is. And we can look at a particle dealing with what we call fictitious centers of mass for the particle aggregates. We know that if I got planetary systems, things are far enough away that things are going to work through the line of action through those centers of mass. But this is going to come into play as we make these problems a little more complicated. We're going to have to worry about things a little differently. I want you to recall our conservation principles. We know we have conservation of mass. We know we have conservation of energy. We have conservation of linear momentum. And we have conservation of angular momentum. So when we're going back to that impulse and momentum idea, that we're dealing with that idea of that impulse and momentum, we talked about drawing our diagrams, and sometimes our diagrams are going to want to look at the momentum before, what's happening in the middle, and the momentum after. So think about our impulse and momentum equation. I got my momentum before before, the impulse that's occurring is going to equal my momentum after. And as we start looking at real systems, we want to think through what's happening in the collision. So kind of think through, and remember when we looked at, and you probably saw this in Engineering Physics 1, we saw that in Newton's cradle, right? At Newton's cradle, where we looked at conservation of energy, and we looked at a collision, and then it collided with the second ball, collided with the third ball, collided with the fourth ball, collided with the fifth ball, and all of a sudden, because there wasn't a sixth ball, we saw something happen. And we had to look at, to really understand what was happening in that Newton's cradle, we had to really, really understand what was happening in each one of those little individual collisions. So, conservation of momentum, it's going to be the sum of those external impulses, right? We know if we're playing hockey, we've got that hockey puck, and the action of that hockey puck, even though player A is hitting it from one direction and player B is hitting it from another direction, where the puck is going to go is going to be a result of all those initial impacts on that puck. All those impulses acting on the system. So we want to make sure that it's simplified, and we can look at that. So the equation is referred to as that conservation of linear momentum, right? The before has got to equal the after, and we want to look at those impulsive forces. So we've talked, the book uses an example of a stake on the sledgehammer. Think about a pile driver problem. Think about where those are. The sledgehammer, a sledgehammer is coming in there, and we have to deal with that. So impact is going to occur when two bodies collide. And we know that that's usually over a very, very short time frame. And the shorter that time frame, the larger the impulsive forces exerted on the bodies. That's why we put in safety systems to extend that time out. Think about that diagram where I showed you that the magnitude of the impulse is the same, but if it's a really short time, the forces are high. If it's a longer time, the forces are lower. So we want to do that. Common examples are hammer striking a nail, bat striking a ball, but we want to also look at where the line of impact is, and we're talking about through the mass centers, and we get two types of impact. This is where we deal with actual physical problems. We're no longer looking at just that particle, okay? We're no longer assuming that particle doesn't have space. The central impact, when it happens, it's going to occur along those lines of force. And think about what happens when you hammer a nail. If I make sure everything's in line, the nail goes straight into the wall. If it doesn't align, I bend the nail, which becomes a pain in the tushy, right? Especially if you're remodeling your house. It's a total pain in the tushy. So I want to, if I'm doing certain things with certain tools, I want to make sure that I'm acting along that line of impact. And we're going to call this a central impact, where we got two particles colliding along that line of impact. But then I can get the second one, and we call it an oblique impact. And that occurs when the direction of motion on one or both of the particles is at an angle to that line of impact. As we get more physical size, right, as we start to deal with physical problems, we know we have something that we considered, and we call them glancing blows. I'm hitting off of the edge. I'm hitting that nail head such that I don't have those things lined up and I bend the nail. So we have many, many opportunities where that, what we call the oblique impact, is going to come into play. So we want to make sure that those are in there. So my central impact, I've got my line of action, my center of mass of this particular particle, my center of mass is that particular particle, and we're going to act on a line of mass. And once this happens, so we're going to take real systems now. If I have two cue balls and they hit, nothing really happens to the cue balls, right? But we've seen slow motion pictures, and I've got GIFs here in just a second that's going to actually show it. If I've got two, say, tennis balls hitting, or two basketballs hitting, or two racquetballs hitting, or even two soccer balls at the point of that impact, there's going to be deformation of the ball, right? The ball is going to squeeze together, and it's going to cause, and it's going to deform if they're not rigid. If they're rigid like a cue ball or pool cue balls, or say those really heavy bocce balls or steel marbles, I'm not likely to get a whole lot of deformation. But deformation is part of a real system. So I've got to start being able to include that and bringing it in. And one of the things, and that's why I went back to talk about our conservation, is because when we have conservation of energy, energy before is equal to the energy after. But if I'm deforming something, I'm causing friction inside of my object. Guess what's going to happen? I'm going to have the potential to lose a little bit of energy. So remember back in Physics 1, we had two types of collisions, right? We had what we called elastic collisions, and we had inelastic collisions. And the elastic collision was a special case. And in that special case, the change in kinetic energy was also conserved when I was dealing with my elastic collision. So when we look at those central impacts, so there are two primary equations that we're going to deal when we solve this. And I want to look at our equation here. So let's kind of take a consideration and let's look at this. So let's look at our collision in phases before we get to those two types of equations. One, before the impact, I got two balls, all right? And these balls are not rigid in perspective in terms of rigid, but I got two rigid balls. And we're going to make the assumption, just for this diagram to work, that the velocity of 1 is greater than the velocity of 2. So, before the collision, we got our two balls. They're coming together. Think playing marbles, right? Think playing marbles. Think playing cue balls. At the point of impact, the impulse of the first ball is going to hit the impulse of the second ball, okay? And I'm going to use the P for a push here. And we've got this impulse, and this is going to start the deformation phase. Now, at phase 3, the deformation is maximum. My ball is going to have, the ball that's coming off is going to start to deform, right? Because it's got the forces being applied to that ball, and then it's going to go on out. And we're going to get a recoil and a restitution of the ball, right? Think of your ball potentially as a spring. And we know that we can look at the recoil and the restitution. And ultimately, I'm going to have that we're going to deal with the velocity after is equal to the velocity after here. And we know by experience that the velocity on ball 2 is going to be greater than the velocity of ball 1. And if they travel off together, we know essentially if those masses are the same, we know that the other ball is going to travel off with the velocity of the first ball. Provided I don't lose what? Energy. Okay? And for the most part, like we saw back in the laboratories that we did, I get good conservation of energy or conservation of momentum. Yeah, there's some experimental stuff, but we know that we can actually see it. So it does help if we look at those phases of a collision. So I've got my gifts here. So up in here, this is an elastic collision. I'm not getting any deformation here, right? And it's just going to go off, and we know how that ball's going to react. I do like the cherries here because it does show you that I have conservation of momentum. And you can see the water balls, the water droplets, and how those apply. So that's pretty cool. But let's look at the tennis racket and the tennis ball at the bottom. The tennis racket comes in. I got really good deformation of that tennis ball. The racket even deformed, but the deformation on the racket is a little bit different than the deformation of the tennis ball. So you can actually see that deformation phase and then the recoil and reconstitution phase. So we're looking at our problems, and the whole reason we do this is we want to determine whether or not we're going to have an elastic or an inelastic collision. So we know with that central impact, we get the momentum before is equal to the momentum after. We have to carry those things too. But what we're going to look at in comparing those velocities, the unknowns, will help us determine our coefficient of restitution, or E. And that's going to let us know, do we have a elastic collision, or a fully inelastic collision, or something in between. Okay? That's what that's going to let us know. So we got our coefficient of restitution. You can rearrange it. Your book actually goes through and does the whole derivation. But we end up with this value, E, and that's our coefficient of restitution. And we can also call, what kind of an impact is it? Is it that total elastic impact, or something that from a material standpoint we're going to call a plastic impact? And we got typical values of E, okay? How steel on steel is going to be there, or lead on lead, or wood on wood, or glass on glass. And you can actually look at that, and the plastic impact is a separation of velocity that stick together, and we have a common velocity after impact. So how are these things going to stick together? So it goes back to that particular aspect. We know we can have energy losses. Remember, in an elastic collision, we actually showed, and you can go back and look at your general physics book or your engineering physics book, and actually see that we could prove that it's 1/2, that the change in kinetic energy is conserved when we're dealing with an elastic collision. Inelastic collisions, not so much, or in our case, dealing with an E that's not equal to 0, or not equal to 1, right? Let's go back. My elastic impact, E has equal to 1. A perfectly plastic impact, where the particles stick together, a perfectly inelastic collision is going to be 0. A perfectly elastic collision is going to be 1. And real world collisions are somewhere in between, right? Real world collisions are somewhere in between. And so we get that, and we get energy loss is going to be a maximum when that happens. So we know that that's there. So let's look at oblique impacts. Oblique impacts are going to be a little bit different. We're going to have 4 unknowns, both the magnitudes and directions of the final velocities. We're going to end up with 4 equations that we're going to have to deal with, and we're going to have the particles that we have to work with. And as we start working the example problems, I think some of these concepts are going to become clearer and clearer. So you kind of need to kind of look at it, and I encourage you to go back and look at those example problems, because I'm trying to break up these lectures so that they're not overwhelming all at once. But my oblique impact is going to have to look at those angles. And we're going to look at how to approach these problems over, as we start doing some examples. So in the procedure for analysis here, you're still going to have to draw your picture. You're still going to have to look at my coordinate systems that you're wanting to look at. We need to know what we know and what we don't know. All right? We want to define our axes. And one of the tricks here is we want to define the x-axis along the line of impact and the y-axis perpendicular to the impact. That's going to simplify our problem. Just like when we set up our coordinate systems on an inclined plane, we want to simplify our problem by looking along the plane and perpendicular to the plane. Same thing that's going to apply here. We want to set up our axes along the line of impact and perpendicular to the line of impact. We want to look at central and oblique impact problems. We want to apply the equations along the line of impact. And then we have to bring into account the things that are happening for our oblique equations. So again, I'm going to encourage you to look at the examples in the book and look at the worked examples as I get them posted, and so that you have those there. So hopefully this gets you started with Chapter 15. Think about those pieces where we had to deal with our phases of our collisions, because that's really important as we go through that. And then I will post the rest of the lecture as we go on.